Hello, everyone. We're going to discuss section 6.3, the development of quantum theory. Um, Before I get into the learning objectives, I just want to say we're going to do a bit of a quick drive-by of this material. It is very complicated, very difficult to get your mind around how this stuff works. Um, and we can kind of skip through most of it and get to the conclusions. This is something, however, that if you would like to, you could discuss as part of a project later in the semester. So the learning objectives extend the concept of wave-particle duality that was observed in electromagnetic radiation to matter as well. Understand the general idea of the quantum mechanical description of electrons in an atom, and that it uses the notion of three-dimensional wave functions, or orbitals, that define the distribution of probability to find an electron in a particular part of space. And then the last one there, we are only really going to talk about two of the four quantum numbers, and not really about the relationships between them. So quantum theory is looking at the behavior of things like electrons and the way they interact with light. And it turns out that they act very, very differently than we do. And the difference is such that it's really hard to believe that it's true, but the evidence that we have suggests that that's the way it is, that electrons are in fact very, very different than we are. So again, we're going to kind of drive by a lot of this. The first idea here is in terms of the behavior of the microscopic world, is that we're used to thinking of waves and particles as being different things. And it turns out that when you get to things the size of electrons, there's kind of an overlap there where they can actually be both. Similar to how light is both a wave and a particle, electrons are both waves and particles as well. This is not what actually happens, but it's a way of kind of visualizing how an electron can be a wave. So we're showing how, at a certain distance, we have kind of this wave going around. This is often called the de Broglie wavelength, based on the person involved in that discovery. Again, we're not going to focus on the equation, but the idea is that the electrons themselves are actually behaving as waves. And part of the implication of this is, again, only certain values are allowed. And this is because if you think about when we first talked about waves, we talked about nodes. And so you have a node, you have a certain length to the node, and then you could have maybe another node, but you're limited in where that node can be. And so essentially, by having particles as waves, we mathematically end up with this situation where we have only certain values allowed, which corresponds with having energies that have only certain values allowed. There are some interesting experiments here showing that electrons are both waves and particles, and how you try to observe them will determine which way they are behaving. This is something I'll let you kind of look at on your own. I'm not going to be testing you over that material. But it's something that's very interesting, and someone could do a project on it later if you would like to. Okay, another way of understanding what's going on here is if we think about understanding what matter is doing. If you think about physics, what you do in a physics course in terms of predicting where things are going to be using math, or as an example, when somebody hits a baseball, they know, what the launch angle is and how far it's going to go, and they can make calculations and know where things are going to be. It turns out for things the size of electrons, that is not possible. It is not possible because of this idea of the Heisenberg uncertainty principle, which is something I think many of you have heard of in some degree or another. And the idea here is that it's not possible, it's not physically possible to know everything about something at the same time. So in this case, we say the momentum and position of a particle at the same time. And so they're limited by this equation. And we're not going to use this equation, but the result of this calculation is that something that is very small has a much larger uncertainty than something that is large. So something like a baseball would be very large here, and the uncertainty in its position would be very small. Whereas something like an electron is very small here, so the uncertainty in its position would be very large. So the smaller something is, the more uncertainty about its position. And this is for moving things. The smaller a moving thing is, the greater the uncertainty about its position. And this really only becomes important when we get to something the size of an electron. It doesn't really matter for things that we can actually handle ourselves. Again, we're not going to get into the details of the math here, but something you can explore further on your own if it's of interest to you. So the quantum mechanical model of an atom is taking these ideas and trying to use them to explain what the electrons are doing. And we essentially think of the electrons as having what's called a wave function, which is a description of where we're most likely to find the electron. Again, we can't know both the position and the momentum of the electron, so we can't think of it like a planet going around the sun. It doesn't have that kind of predictability to it. All we can talk about is where is it likely to be, and we can draw pictures showing shapes of where it's likely to be based on some complicated math. So this is the study of this is called quantum mechanics. This equation here is fairly complicated math. It might not look complicated to you, but this gets into some calculus actually. So it is fairly complicated, and we're not going to cover it in this class. But we will we'll look at the results of the calculations from that. So the results are going to be quantum numbers. And the one we're going to care about is the principal quantum number. And that's essentially the energy levels that we've already referred to. So these are quantum numbers, so 1, 2, 3, etc. And you can think of it like, shells around the nucleus, where we have electrons somewhere around here, we have electrons somewhere around here, etc. as we go out. And so think back to the Bohr model where we have the different energy levels. This is essentially what we're talking about with the principal quantum number, are those different energy levels. And so we've seen this before. The additional quantum numbers, and again, it's showing them here, we're not going to talk about the numbers themselves in too much detail, give rise to the actual shape of the space where the electrons are located. So we have names for these different kinds of shapes. We call them orbitals. And it doesn't mean like a planet orbiting the sun. It's just the name that we have arrived at to describe these. So we can talk about the orbitals in terms of their shapes. Okay, so we have the s orbital is something we're showing here. It has a spherical shape. Don't worry too much about the difference between, this is a 1s, a 2s, and a 3s. The main thing you want to notice there is as you increase, so the 1 being the principal quantum number, as you increase that, you are increasing the location where the electrons can be. So they get further and further and further away from the nucleus. Okay, so those are s orbitals. We can think of as being kind of spherical in shape. We also have what are called p orbitals. So in a p orbital, what's going on is you have the nucleus, and around the nucleus you have these lobes. So with an s orbital, there is basically there's no node, or there's not necessarily a node, I should say. With the p orbital, there is always a node, and the node is going to be a plane that goes through the nucleus. And so what you have is you have kind of a lobe on one side of the nucleus and a lobe on the other side of the nucleus. And we can have a number of different p orbitals. So we're showing them here. You basically have three possibilities based on having this three-dimensional coordinate system. You've got, kind of to the left and the right. You've got above and below. You've got front and back. So those are the three different lobes. Technically, they're called P sub x, P sub z, and P sub y. I'm not going to care that you match the name to the picture for that, other than that's what a p orbital will look like. We also have the d orbitals. There were 3 p orbitals. There are 5 d orbitals. And for the d orbitals, we have, even more complicated shapes. In this case, we have at least 2 nodes. So we're showing that by showing basically 4 lobes. So you have a node that goes typically 2 nodes that are kind of 90 degrees apart from each other. So going along 2 different axes, and they intersect at the nucleus. So we've got this one, and this one kind of follow that pattern. This one too, to some extent. And then we've got this other one that's a little bit different. It's kind of like a donut around the nucleus with a lobe above and below it. So we have 5 possibilities for d orbitals in terms of what they look like. Again, I'm not going to care too much that you remember these, the names for these for now, but that's what d orbitals are. This textbook actually has a picture of the f orbitals. Most textbooks do not. And these are essentially, don't even try to remember all of these. These are just even more complicated. So there are 7 f orbitals, even more complicated than the d orbitals. So just kind of let that be your understanding of f orbitals. They turn out to not be all that important for most of what we will be discussing, even though there are many of them. So these different orbitals are related to different quantum numbers, and we're not going to worry too much about these quantum numbers for now. What we are going to end up doing is talking about where those electrons then end up related to, there'll be electrons in these different orbitals, and what does that look like related to their energy. That's something we'll be getting into in the next video. The last quantum number I want to talk a little bit about is the spin quantum number, which is shown as m sub s. It is actually not related to the other 3. The other 3 are mathematically related to each other. This one is different. And the idea here is that the electrons are spinning, or they're doing something that we would associate with spinning. We don't know for sure if they are spinning, but we know that the physical effect they have on their environment would be consistent with a charged particle that is spinning. And it turns out that there's basically 2 ways they can spin. We call it spinning up and spinning down. We don't have to know what that means for this class, other than there are 2 possibilities, and we give them a +1/2 and a -1/2 in terms of describing them. With the spinning of these electrons, the thing that we need to know about that is that they will pair up based on having opposite spins. And that's something that will affect the way they form bonds. And one way of describing that is with something called the Pauli exclusion principle. And this is something we'll talk about a little bit more in the next module. But the idea of the Pauli exclusion principle is that the 4 quantum numbers cannot all be the same. And what that means is that for any orbital, you essentially have to have two different spin quantum numbers. So an orbital can have up to 2 electrons in it, and the number of orbitals and how they fit together with the principal quantum number is described in this table. Again, we're not going to worry about this table. How we will describe it is by talking in the next section about electron configurations. So that's where we'll leave off for this one, and come back to the next video to learn about electron configurations.